Let me check one more thing. All right. Yay. So before we jump back into our notes and look at a whole bunch of crazy trig stuff, let's just touch base on the writing assignment. So this was practice reading the words, translating it into the mathematical notation, and then answering, evaluating what each of those limits are. So this first one, the limit of f of x. So we have our limit. We have f of x as x approaches 2. And then from the left is negative infinity, so we give it a minus sign after. And now we'll actually look at that. So here is our 2. And then from the left side is coming from this direction. So we want to see what is the graph doing. And it's coming in and getting real close here to a function value of 3. Now we're going to do the other side. The limit as x approaches 2 from the right. That's from the positive infinity side. And from the right side, our function is just doing this flat line thing. And that flat line is at positive 1. So the limit from the left is 3. The limit from the right is 1. So they both exist. But what does that tell us about the third question? What's the limit as x approaches 2?
Does not exist.
Yep. So anytime we're asked what an overall limit is, we need to follow these same steps. Consider the left, consider the right, consider if they're the same. So when we're looking at the limit as f of x approaches negative 1, all right, there's our negative 1. So as we approach from the left, what's the graph doing? So on the left side of negative 1, the graph is shooting just down, down, down. So what do we call it when it shoots down like that? Yep. So on the left side, it's going to negative infinity. But what's the graph doing on the right? It's coming in for a landing at 0. So the left limit exists, the right limit exists, but they don't equal the same thing. Now, at negative 3, as we approach from the left, the graph shoots up, up, up. As we approach from the right, the graph shoots up, up, up. So what are those two limits equaling? Positive infinity. Now we had some mistakes on the last two. That's okay. Really, the purpose of the writing assignment is to kind of get y'all's mistakes out of the way before the exam. So the writing assignments are worth far, far less on your overall grade than the questions on the exam. So if you didn't do as good as you would have liked on the writing assignment, like treat it as a, all right, lesson learned. I won't make those mistakes on the test. So I don't want y'all to feel discouraged if something happened. Like the whole purpose of the writing assignments is to cause something to happen, as weird as that sounds. And overall, they're really not going to impact your grade that much. And a good chunk of the grade is still coming from completion. So you're still getting a fair number of points on them as well. So what questions do y'all have on that? All right. I guess everybody's like pretty practiced at submitting digital stuff now, so at least that part of it wasn't as much of a problem. I still got a fair number of messages from my pre-cal students. How do I submit this online? I'm like, well, you fold up the paper and shove it in the CD-ROM drive. Oh, wait, no. And some of y'all are like, what the heck's a CD-ROM? I'm old. All right, so we had been in the middle of this one when we had to break last time, so let's see if we can't clean that up a little, finish it off. What in the heck is 12 times 81? Honestly, Chris, you pick the weirdest numbers. $972. Good Lord. So we end up with an ugly quadratic on the bottom, but for these calculus problems to work out, on top, both of the factors had a 9 in common, so I factored that out. And that means one of the two factors in factoring the quadratic should be 9x plus 109. So I'm going to fill that in, and then I'm going to like figure out what the other half would be, and then just make sure it works. So I'd have to have an x here to get 9x squared. And then 1308 divided by 109 is 12. So trying to factor that disgusting quadratic on its own is like a ridiculous exercise in futility. But the way these problems are designed, they're set up so we should have some cancellation happening. So you work a little more strategically. On top, I factored it down as much as I could, and then I said, aha, there's the thing that's supposed to cancel. So let me get rid of those. And now I'm going to write back in my annoying limit. Now we can substitute that number in, and that result is the answer. So we would have 9 divided by, open parentheses, negative 109 over 9 plus 12, and then close the big parentheses. And that apparently equals negative 81. So that is a ridiculous amount of work to get a number. That is absolutely way too stupid for an exam. It's almost way too stupid for a question in class, but I can't think of a question that would get uglier than this. So the good news is all of the homework should have looked less ugly than this. Especially, we really don't do, like, you can do a limit as x approaches any number you want. So we can have a fraction in there. But typically, we try to keep the numbers that the limit approaches to be a whole number, just so that's like one less extra annoying thing y'all have to deal with. But technically, the limit can't approach any number. So overall for our limits, the first thing we want to try is plugging in the limit value. If we get problematic math from that, where we get typically it's a 0 over a 0, then we want to try factoring, rationalizing, or simplifying the complex fractions. So that's like one half of the things. And then the other half of the things, we start with this squeeze theorem. So here I've got my graph on top is pink, my graph on the bottom is blue. And like the first question is, how many different graphs could I draw that exist strictly between these two lines? So I could like draw a graph that's like, I'm going to doodle around, I'm going to do whatever I want, but oh, there, now I can do whatever I want again. If I try it a different way, all right. I'm just going to be sneaky, jump up here, jump up. Oh, I'm stuck. All right, now I can do what I want. So whatever crazy graphs we draw in between those two lines, eventually they're getting railroaded in this region at x equals 2. So where the pink and the blue graphs are actually coming down and meeting at a particular point, so they're both actually equaling that point there in the middle. Any other equations that I can prove are strictly between two equations, the pink and the blue. Whatever the pink and the blue are doing at that x value, all the other graphs are forced to do that. So we can use this squeeze theorem to actually help us out with some annoying trig graphs. So here's the very formal mathematical definition. So if we know that g of x, so h of x was our pink graph, f of x was our blue graph, and then g was whatever graph was in between. As long as we know for sure that g is always in between those two, then if f of x and h of x are approaching a limit value, then g of x is also forced to equal that same limit value. Now, this isn't something you're going to have to use in practice that much. This is more like a behind the scenes that happens to give us a couple of extra nice limits that we use. All right, now this one is not a limit we use a bunch necessarily, but it really showcases how to use the squeeze theorem. So the first thing I find when you're looking at these is to actually pop over to Desmos and see what the heck it looks like. Now that is just weird looking. But it appears as we're getting closer and closer to zero, that this one is getting closer and closer to zero as well. Now, one of the things to remember about our trig graphs is the graph of sine of anything, whatever's on the inside, the sine graph is always bounded above and below by its amplitude. So I'm just going to write sine of u because that u can literally be anything. And all right, not the best picture, but the absolute highest a sine graph gets, if it doesn't have a modified amplitude, is 1. And the absolute lowest it gets is -1. So sine of whatever ugly mess is always bounded above and below by 1 and -1. So I can literally write that as an inequality. Now, when I'm looking at the formula I have here, the x squared sine of 1 over x, I'm just going to take this inequality and multiply everything by x squared. So I end up with -1x squared has to be less than or equal to x squared. Sine of ugly has to be less than or equal to +1x squared. Now the ugly I wrote in here, I'm going to change it out for what we had in the graph, which was the very stupid 1 over x. So trying to directly evaluate the limit as x approaches 0 of this, sine of 1 over x, like constantly changes values back and forth, back and forth, back and forth. So the limit as x approaches 0 here doesn't exist. It's confusing. But when we multiply it by x squared, the x squared as we get closer and closer to 0 gets closer and closer to 0 itself. But just looking at those two, it's hard to say which one of those has more control over the limit. But when we compare it to these other two, 1x squared and -1x squared, these are going to sandwich the graph in, squeeze it in, and force it to go to 0. So if I do the limit as x approaches 0 of -1x squared, well, it's just a simple polynomial. I plug it in, I get 0. I do the same thing on the right. I also get 0. Therefore, the limit as x approaches 0 of the ugly mess in the middle is also equal to 0. Now, figuring out what to put on the bounds there, that's the part on the squeeze theorem that can get a little weird. And it's not typically something we put on the exam because it's not always obvious to people what to pick for those two. Like here, we very much used the structure of the problem and the fact that trig functions, sine and cosine, are always bounded by -1 and 1. So we just exploited that to our advantage. So questions on how that worked out. The graph, how I picked those bounding functions, how we got to the conclusion. All right. So some of our important results that are proven in the textbook. So the first two, the limit is sine theta equals 0 as theta approaches 0 is 0. Yay, because that's also literally what you get when you shove 0 into the function. The same thing, the limit is theta approaches 0 of cosine of theta is 1. Good, because that's what you get when you put 0 into cosine. Then we get this weird limit, sine theta over theta. So the limit is theta approaches 0 of sine theta is 0. The limit is theta approaches 0 of theta is 0. But the quotient of these two actually equals 1. These two values are getting closer and closer to 0 at exactly the same rate. So the quotient of them actually divides out to be 1. So this is one of the limits that we are going to use a ridiculous amount in the next examples. So this guy is like our best friend. Then this guy here that we're going to prove is our other best friend for trig limits. Now, Chris, when they write their notes, they like to put little hints at the bottom. And sometimes they're useful to figure out how to start the problem. Sometimes they're just more like, okay, I'm going to have to use that at some point. In this case, though, we start with a cosine equation, but remember at the bottom is the sine one, that sine theta over theta equals 1. So somehow we're supposed to turn this weird looking thing and we're supposed to get a sine out of this. But first thing first, let's just check what happens when I plug in 0. I have 1 minus the cosine of 0. Cosine of 0 is 1, so I have 1 minus 1 over 0. I get 0 over 0. All right, so we were sure. All right, so direct substitution does not work. Not a surprise. So now we got to figure out something else to do with this weird mess. Now, this is where we're making use of some of those skills that we were practicing in pre-cal when we were doing the trig identities. So 1 minus cosine theta itself is a little weird, but what it does have a nice property with is the conjugate of it, 1 plus cosine theta. So seeing that this is what you're supposed to do is weird. But now that I'm telling you, this is what we're going to do here, now you should be able to follow through the rest of the algebra and the trig to do the rest of this. So on top, that is a FOIL situation, but it's a difference of squares. So let's rewrite our limit again, because we're technically supposed to write that every time. But on top, we're going to have 1 minus cosine squared theta. That should sound a little more familiar. And on the bottom, don't multiply it out, just leave it factored. So 1 minus cosine squared theta, what is that the same as? Yep, sine squared, because sine squared plus cosine squared is 1. So that is what we're going to do next, is we're going to make that substitution. So we still have the limit, but now it's sine squared on top. Now our remember at the bottom is having a little more impact. So I'm going to take my sine squared theta and I'm going to split it into sine theta times sine theta. And I'm actually going to split the bottom, like I'm going to split this into the product of two fractions. So right now I still have one limit of this giant product. But one of our rules with limits was the limit of a product is the same as the product of the limits. So I can distribute that limit across the multiplication. So I can write this as the limit as theta approaches 0 of the first fraction, sine theta over theta, times the limit as theta approaches 0 of the second fraction. Now this first limit is proven in the book that it's 1. This other one now I'm going to substitute in 0 and they're going to work out. So the limit as theta approaches 0 of sine theta, sine of 0 is 0. And then cosine of 0 is 1. So we have 0 over 2, which is 0. 1 times 0 is 0. So a whole lot of work to get a 0, but when we tried it the direct way, we got 0 over 0. So this is the other trig limit that's going to pop up on occasion. So seeing that first step that you're supposed to multiply by the conjugate is a little bit weird, but all of the steps after that should feel comfortable, especially after you get some practice on these in the web work. Or at least familiar. Like that right there is a real example of how calculus homework is. There's like one weird step at the beginning, a whole bunch of algebra and trig stuff, and then one calculus step at the end, answer. So that's why you had so much homework, so much practice in the previous courses, is because so much of your work in this class is the work from the previous courses. All right, now this one. If I plug in 0 right here, we'd have tangent of 0 over sine of 0, both of which are 0 at 0. So we end up with an indeterminate form. Okay, oh crap, I got to do something else. All right, so one of the first things we're going to do is trade out tangent for sine over cosine. Now that fraction like that looks like an ugly mess. So one of the first things I like to do is just slide that sine 3x over, so I'm looking at a fraction times a fraction. So now cosine of 0, 4 times 0 is 0, cosine of 0 is 1. So the cosine's okay, but the sines now, we're still going to get 0 over 0. So we need to do something else to mess around with these. Now this is where our best friend sine theta over theta equals 1 is going to come into play. Now the way this limit works, theta is a placeholder for anything as long as that anything also approaches 0. So when I have sine of 4x in my limit down here, if I had the limit as 4x approaches 0 of sine 4x over 4x, it would equal 1. So we're going to pattern match. Let me just kind of highlight that. As long as sine of ugly over ugly, as long as the uglies are the same, the limit as that ugly goes to 0 is 1. So we are going to try to pattern match and get those uglies to be the same. Now we're going to end up with some extra pieces floating around, but this is how we solve this particular mess. All right. Every freaking time. So I'm writing it a little bit different, but what I'm going to do now is I'm going to start multiplying in by stuff. So to start pattern matching, I need an x on the bottom of these fractions, or on the top of this fraction. So I'm going to multiply by x over x. But I'm going to kind of sneak that back in up here. So now I'm going to write in those x's here and here. So now my sine 4x over x, it's not a perfect match. I really want to see a 4x on the bottom. I need those to be exactly the same. But if I want to put a 4 on the bottom, the only thing I can do here is multiply by 1. So because I'm wanting to see a 4 on the bottom, I'm going to multiply by 4 over 4. So this 4 is going to come in on the bottom and end up incorporating in there and then end up becoming a 1. The 4 on the top is actually going to end up being part of our answer. And then similar idea here on the last fraction, except what I want is a 3. So we've got all of that. I don't know what Chris's other method is here. Like, this is the only way I got to do this. So now I'm going to regroup again. So with my 4 over 4, the 4 on the bottom came inside the fraction. The 4 on top is staying outside. With my x over sine 3x, the 3 on top came inside. The 3 that was on the bottom, the 1/3, stayed on the outside. Now we're going to actually do the evaluation of the limits. So sine 4x over 4x, ugly over ugly, sine ugly over ugly, this is going to be 1. The 3x over sine 3x is technically 1 over 1, but that's still 1 when we evaluate the limits. The limit as x approaches 0 of all the rest of the pieces, we can do the direct substitution. So this will be 1 over the cosine of 4 times 0. Cosine of 0 is 1 times 4 times a third. So we end up with a result of 4/3. So this is a whole lot of algebra tricks all in one problem. It can get very trippy. And the kind of the weird thing is if you look at the original problem and then you look at our answer, it's like, oh, it's just the numbers inside. Yeah, sort of. Like it does end up being that way, but it's not a perfect match. Like it doesn't always just equal those coefficients. But probably about 90% of the time, and probably on almost all of your homework, it is. So if you're running out of time and you're like, I'll just try something, 4 over 3, answer, cool. So there's technically 2 more of these ugly messes, but we only have 5 minutes left. So let's go ahead and see if we can't do this one. Or do we have more time? Am I bad at my math today?
Yeah.
Oh, we started at 10. Yeah, we got time. Damn. I am so used to ending at 50 that I forget this goes to 11:15. Yeah, we got time. Okay, rewind. Just kidding. So now some of those trig identities are coming back to haunt you. You thought you finished pre-cal, they're gone. Nope, nope. I tortured you with all of those for a reason. So we got to remember what's cotangent, what's cosecant. All right, so cotangent has the t in it. So we know this is 1 over tangent. And then hopefully we remember tangent is sine over cosine. So the reciprocal of that is cosine over sine. So cotangent of 3x is the same as cosine 3x over sine 3x. Now, what about the cosecant? Yep, cosecant's 1 over sine. So cosecant of 8x is 1 over sine of 8x. So I've got a couple of sines in there. I've also got those x's, and I've got that cosine of 3x. So again, the cosines usually are not our problems in these. Cosine of 0 is 1. 1 is a lovely number because it's a number. It's not a 0 or an infinity. Now, if everything approached 0, we're perfectly fine getting 0 as a limit. But usually in these, we get some mix where it's a 0 over 0 situation. So what we're going to do is this x squared, I'm going to break it apart. I'm going to put one of them here with the sine 3x and one of them here with the sine 8x. And then that cosine of 3x, I'm going to write in front. So like not outside the limit, just I've got cosine of 3x. And now I've got times x over sine 3x times x over sine 8x. So I said I was distributing the x squared. That is the wrong word. Distribution only happens when it's multiplication across addition or multiplication across subtraction. This is all just multiplication. So really, I was just breaking it apart and rewriting it. So if I multiplied this back, x times x is x squared, and I could write that out front. So still equivalent. Now we want to pattern match our x over sine 3x. I need to see a 3 in here. But I can't just throw a 3 in there. I have to do it in a balanced fashion. So I also, if I'm multiplying by 3, then I also need to divide by 3, which would be multiplying by a third. The same with our sine 8x. I want to see an 8 here. That's multiplying by 8. So I need to balance that by dividing by 8, which is multiplying by 1/8. Now, when you're looking at your notes later, if you're only writing in one color of pen, this can look just like poof, the 3 and the 8 just like came out of nowhere. That's why I use the colors in my notes. So you may want to like add some arrows or something, write a little note to yourself like these were added after, like we put this in because of that. So now our 3x over sine 3x, our uglies are the same. That's going to be a 1. Our 8x over sine 8x, also going to be a 1. So now, sorry, no more limit. We're actually plugging in. We have the cosine of 3 times 0 times 1/3 times 1/8. So the cosine of 0 is 1. So we have 1 times a third times an eighth. So we get 1/24. So these trig limits can look very intimidating on first glance, but they are making use of the same few trig limits. And it's very often the sine ugly over ugly. So what questions do y'all have on how this one shook out? All right. Now this last one, we're seeing t minus t cosine on top. Like we're also going to make use of the cosine limit in this one. Well, are we? Yes. Sorry, first look, my brain thought it saw a different way to do it, but then I realized that this is cosine of 14t, and on the bottom, this is sine squared of 16t. So even if I changed out the bottom and wrote it as 1 minus cosine squared, I can't get a cancellation between the top and the bottom because they're not of the same variable. The 14 versus the 16 screws that up. If they were the same variable, then that is absolutely a way to attack this one. All right, so let's think about how to write this. So first thing I'm going to do is factor out that t on top because it just looks weird. So I'll have 1 minus cosine of 14t. Ugh, way too many parentheses. All right, so I split this apart this way because in my head I'm thinking about like these are parts of those weird trig limits that I see. But this kind of thing happens very often where we're missing the variable part that normally shows up on the bottom of the fractions. But in this case, since I have 1 over sine of t, okay, then I'm missing a t on top, and then the 1 minus cosine of 14t is missing a t on the bottom, and then we'll deal with the numbers. So I'm going to multiply by a t over t. Now, again, without the colors, it looks like I just threw those in there and they came from nowhere. But I'm making this choice deliberately after I broke them all apart into individual fractions. Now, I also need to attend to the number parts. So I've got t over sine 16t. I need this t to have a 16 on top. But I also have to balance that by a 16 on the bottom somewhere. Now I have to do the same process on the second fraction. So I'm going to put a 16 on top and I'm going to multiply by another 1 over 16 to balance that. So I'm still multiplying by a weird form of 1. Now our cosine limit, 1 minus cosine ugly over ugly. My ugly was 14t, so I need to see a 14 on the bottom of this guy, which means I have to balance that by multiplying by 14 on top. So now at this point, it's really easy to get overexcited and be like, oh, I see what the answer is going to be. It's 14 over 16 squared. And almost. So what does the 16t over 16t, what is that going to equal when we do the limit of that? Yep, 1. And then the second 16t over sine 16t, still 1. But what about the 1 minus cosine ugly over ugly? What does that tell us it equals? I heard someone out there say it's 0. So I got 1 times 0 times ugly mess. Doesn't matter what those numbers are. This product is actually 0. And this is why you're not going to see a lot of questions that have the 1 minus cosine ugly over ugly, because then the whole limit goes to 0. But if the cosine one wasn't there, yeah, we would have ended up with 14 over 16 squared, which reduces slightly. All right, so let's see what some of this web work homework looks like. Or I should actually open it up. So those of y'all, oh my God, 18. Ugh. Sorry, I was looking in the homework 2.3 part 1. Question 2, like it's two little annoying looking graphs, and then you scroll and you're like, "Oh, I got to answer a few questions, a few 18 questions." I did not write this. That being said, it is good practice because this is what the test question typically kind of looks like, is we give you two graphs and then we ask questions based off of the graph. So getting this practice of reference back to the graph, interpret what the question was, pull the information I need, that is still good practice. So as annoying as 18 of them is, it is good practice. Yeah. Okay. Right. Annoying, but not the worst. A little more work, a little more work, a little more. Yeah. Yeah. All right. So, like we are out of notes. If I scroll down here, it's just a summary. Like here's the big trig limits, a little bit about squeeze theorem. So this is the point where those of y'all who have been working ahead or just doing work, Are there any questions in the web work that you're like, this question is driving me crazy? Please, 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 can we look at it?
9 and 10 on 2.2, part 2.
So 2.2 part 2, 9 and 10. Right, so here's what I got for problem 9. So this one is asking about the left and right limits of a value for secant of x. So this one, you want to be familiar with the graph of secant of x, which we can pull that graph if we remember what the graph of cosine of x looks like. So we're going to do a little bit of like really bad hand sketching. So cosine of x graphs like this. Starts at 1, hits 0, -1, 0, 1. So that first 0 occurs at pi over 2. If we backtrack it then, the 0 over here occurs at -pi over 2. And I'm focusing on that because that's the value this one asked about. And they're typically, when they give you this kind of question, typically what they're focusing on is an asymptote in the graph. So that's the graph of cosine of x. So that means the graph of secant of x, everywhere cosine is 0, we have an asymptote. Everywhere cosine is 1, secant is also 1. And then it goes and hugs the asymptotes. So our first one is we're approaching -pi over 2 from the left. So from the left, we look at our secant graph, and it's shooting down to -infinity. But then we're going to look from the right. So as we're approaching -pi over 2 from the right, the secant graph shoots up to positive infinity. So I got a negative infinity and a positive infinity. So what does that mean for my limit overall? Does not exist because they're not the same infinities. Now, if they both approached positive or both approached negative, then we could say, yeah, it equals that. But because we're not actually getting a high five or a low five, we're getting a flip, a split, overall does not exist. Now, they also might have asked this with cosecant instead, but it would have been at, again, one of the asymptote values. Eh. And this is definitely the moment where you're like, yeah, she doesn't write these problems. Because that's my reaction when I look at some of them. I'm like, what were you, why? It's not that y'all can't do it. Y'all can do it. It's just a, why? So when we plug in the natural log of 3, e to the natural log of 3 is 3. So on the bottom of all of these fractions, we're getting 3 minus 3, which is 0. So what we're getting here is some sort of asymptotal behavior. But whether they're both going to the same side or opposite sides, hard to tell. So for this, I'm literally going to Desmos and graphing it. Now we could figure out what the decimal of natural log of 3 is and plug in numbers a little bit smaller and a little bit bigger into the algebra fraction. But if you're doing all that like number crunching on your calculator, you may as well just look at the graph, especially for a question like this. Like that is way too stupid looking an equation for an exam.
Good. First,
So we've got 8 plus 12 e to the x over 3 minus e to the x. All right, so let me flip the share here so y'all can see the Desmos. So originally I was actually zoomed in and saw absolutely nothing. I zoomed it out and I was like, oh, okay, so the graph is doing like a weird splitty thing. And then I was like, where is natural log of 3? So I typed in x equals natural log of 3 because we're as x approaches this number, so this vertical line is the limit the numbers we're actually approaching. So now that I'm looking at the graph, as we're approaching the natural log of 3 from the left, the graph is shooting up to positive infinity. As we approach from the right, it shoots down to negative infinity. And then those two are not the same, so overall we're going to get it does not exist. Now, if I plugged in, like apparently natural log of 3 is 1.09. So if I plugged in like 1.08, even 1.097, 1.0985, like plugging in close to an annoying decimal like is awkward. But you would get like ridiculous huge or ridiculous negative numbers on either side. So let me, you know what? Let me even do this. Flip back over to the notes. Flip the share back. So again, this equation is far too disgusting for a test, but it's not bad for a homework question. I'll also say it's not good. Like if I was going to tweak this question, I would put, go take a look at the graph of this thing and then answer the questions, because doing this algebraically is annoying. All right, so we're going to talk about continuity next and then limits at infinity. All right. Are there any other questions in the web work that you guys have gotten to that you'd like to see? Here, let me flip the share over to this one from the 2.3, the one that I had the sticker shock on. So problem 2, like I said, it starts and you're like, that's not that bad. Here's the graph of f of x. Here's the graph of g of x. And then you scroll. Yeah. And I want you to notice some of these, like, 14 here, that is f of x divided by g of x. But it's all written on one line, so it's really easy to mistake. Like, look at 7 and 8. 7 is the product of the two. 8 is the quotient of the two, but they look very similar. So if you're doing this on a small screen, zoom in so you can clearly see what each question is asking. This is also one of those ones where, like, write down what the question is, then you go back to the graphs, figure it out, write down the answer. Like, it's a whole lot of back and forth and back and forth.
You go through a couple of them.
Yeah. All right, so this first one here, the limit as x approaches 3 from the right of f of x plus g of x. So you know what? Let me actually screenshot this over because I think it'll be easier to play around on OneNote. And that's actually something I'd recommend on this one because you're going to constantly want to look at the graph, but also look at the equations. Doing a screenshot, pasting the graph on like a Word document, and then just having it so you can like look at them side by side would make this a lot better than the scroll up and down all the time. So there is like a quick key to do a screenshot. I know on Windows computer, it's Win-Shift-S, pulls up my snip part of the screen, and then I just drag the rectangle and then Control-V, paste it wherever I want. So that's how I'm poof, like suddenly I have the screenshot. But there's a quick key on Macs as well. I don't use Macs, so I never remember what it is. All right, so as x approaches 3 from the right, so f is approaching 1. And then g is approaching 0. So the limit as x approaches 3 from the right is 1. Now the second part, f of 3 over g of 3, now I don't care what the limits are doing. I am literally just looking for what is the function value at that number. F of 3 is way up here at 4. Divided by g of 3 is 0. That's undefined, so we're going to go with does not exist. It just looks weird when I put it on a sideways fraction. So 2 and 3 are where the interesting thing happens. F of x is really weird at 3, but g of x is really weird at 2. So the limits here are also constantly changing the number we're looking at as well. In fact, really, this is only looking at a few limits, but they mixed up all of the pieces. All right.
So
So any one of these look uglier than the others that you're like, please do this one?
yeah.
I don't know. This is my expert blindness. They all look about the same to me. I mean, like they're all different answers, but they're all about the same amount of cognitive work to me, so I can't tell which ones look ugliest. Well, this is why we have GroupMe. So if something happens and you're trying this out later and you're like, it is not clicking, it is not making sense, hit me up on the GroupMe. I'll absolutely respond. We will make it make sense. Right. Let me go ahead and